Let's get going.
Loosen up, bit of lunges,
Lunges.
action. There you go. Just do it, just
Fine.
go with the flow of the lunges, Molar. Hello and welcome to A-Level Chemistry from the OCR book. The first few pages are mostly just sort of history on how the atom was discovered. It's very useful, but it's not in your exam. It's more just an interesting read. Wayne, do you want to walk through what we're going to do first?
So as Trev said, we're just going to, you can see here the beginning bit is just about the history of an atom, so we're actually going to jump, because there's no questions about this, to page 8 first. You can see, drawn up here, you've got carbon. It's 12 and 6. Now it should be a revision from GCSE. Let's go. This top number is the mass number. That means it's the amount of protons and neutrons in the nucleus of an atom. Now here we have the atomic number. That's the number of protons in an atom. It's also the same as the number of electrons in an atom. So what this really tells us is, firstly, we should have 6 protons in the nucleus. 1, 2, 3, 4, 5, 6. But altogether we should have 12 particles in the nucleus. This implies there's actually another 6, which are neutrons. 1, 2, 3, 4,
This happens
6.
only in atoms and ions, because isotopes have a different number of neutrons, but we'll go into that later.
Now, the bottom number, as I said, is the number of protons, but also, for an atom, is the number of electrons. So in the shells surrounding the nucleus, you should find 6 electrons. 1, 2, 3, 4, 5, 6. You should remember from GCSE, the first shell has 2 electrons, and when that's full, you move to the next, that can have 8. But in this case, it's only got the 4. So now we're going to move on to ions and isotopes next. Similar rules, but we're going to go through them now. Right, so now we're going to run through the rules of ions and isotopes. So I've got the example of sodium.
Okay, well first what an ion is an atom with a different number of electrons, which gives it different charges.
Now you see here, we've got the mass number, we've just been through, is 23. And the atomic number is 11. This implies there is 11 protons.
And 23 protons and neutrons in total.
So that would make how many neutrons altogether? These are the sorts of questions you might be asked. If you're given this number and this number, you've got to say how many protons, you've got to say 11. How many neutrons? It's going to be 23 minus 11, which is simply 12. So we can have an ion, we can have Na+. But what does that mean, really?
Well, the plus means you have lost an electron. Because they are negatively charged, you lose them, you get a positive charge.
Yeah, electrons are each negatively charged. So, but what this doesn't actually affect this. So, whereas isotopes, which we're going to go through in a minute, if you were to write it in this form, would actually change. With an ion, they do not. You'd still write Na23 and 11
because the electrons aren't taken into account into these numbers.
You don't just get positively charged, you can get negatively charged. Let's do a simple one of those, is chlorine.
And if it was negatively charged, it means it gains an electron. As they are negatively charged, it puts a negative charge on the atom.
You do actually get, instead of just 1+, you can get 2+, like magnesium, and 3+, like aluminium.
And we'll go through it later. On the periodic table there is sections where you know one half will be plus and one half will be minus, more or less. And when you get later you'll have much bigger numbers. Perhaps it will say manganese 7. And this will be denoting a +7 charge.
Now let's move on to the isotopes and see how that applies to the rules when you write them in this sort of form. Because this is what we're really focusing on at the moment, is writing it like this and quick revision of what really happens. So, isotopes.
Well, okay, I'm going to talk through carbon 14. Now you should remember that carbon is normally 12.
That's right.
So you've got to work out what to change. When an isotope hits the amount of neutrons in an atom, so you take away the amount of protons from the total.
Yep, so in this case, the normal carbon, as we drew in the first section of this video, you have 6 protons and then divided up quite nicely 6 neutrons. This time, we've still got the 6 protons, because that's what this number represents. We've actually got 14 minus 6 neutrons now, which instead of being 6, like in this one, is actually 8. So, to sum up isotopes, really, what you can say is there's a different number of neutrons in the nucleus of an atom. That's what an isotope is. I think that basically sums up isotopes.
It does. Later we'll go on to how to work out relative isotopic mass, because this is actually an average of all the different types of isotopes that carbon has.
And then we're going to be going on to using ions, because this was just a quick explanation. You might still even be a little bit confused about what they are. We're going to move on to some where these come in use and how to use them.
Yeah.
So let's get going.
Now I'm going to do a question on relative atomic mass.
So we have a worked example here from the book. We're just going to put this on the board. I'll write it up.
Okay, when you see atoms and elements in the periodic table, the top number is the relative atomic mass. That means there's actually the average of lots of isotopes, working out what's maybe the most common would be 81, and the least common would be 20, and it will average them out and give a number. And what we're going to do now is basically what they do in real life and work out the relative atomic mass of these two isotopes.
So what we've been given, much like they've been given in real life to work out the values in the periodic table, we've been told there's this isotope, there's this much of it, there's this isotope, and there's this much of it. So we need to work out the relative atomic mass. That all that really means is what really is the value of this number of bromine. Because it's not 79 because there's some of this one. But it's not 81 because there's some of this one. So what is that number? And that's what we do. So,
okay,
what do we do?
First, we split that up a little bit. So as they have percents, we divide the percentage number we have by 100, and we multiply it by the value of atomic mass we have here, which is 79. Then, yeah, then we add it to what we're going to do on the other side, which is very similar. We divide the 47 by 100, and then we times that by 81. So we go below that. We'll do a quick calculation. Ooh. So this is 41.87 plus 38.07. And that equals 79.94. You won't be doing these things in your head in a real exam. You'll have a calculator, so it'll be relatively simple. And that is our relative atomic mass.
So, like Triv said, in the real world, proper scientists do basically this exact thing to produce a number, and then they put the actual number based on the real percents and the real different isotopes, because there might be more than this. These might not be the accurate percents. They produce the number, and that's the number you actually get in your periodic table. That's how accurate your periodic table is. So that's our work with isotopes. That was atomic mass. Now we can move on to molecular mass first.
Yeah.
So what's that?
So molecular mass actually is the mean mass of a molecule.
So if we take an example of chlorine, which is Cl2,
we know that the mass number of each chlorine is 35.5, and as there's 2 of them, times this by 2, and we get 71.
now there's no units for this molecular mass. It's not in grams or meters or anything. You just leave it as a solid number. That is your answer. You put that on the answer bar. That's it. Where did we get 35.5 from? Well, Triv, where did we get it from?
Well, you get a periodic table in your exam, magical thing, and on top of each of your elements it says a number, which is the relative mass, and it is 35.5 for chlorine.
So if we go on to another example of water, H2O, what do we do here?
Well, very similar to what we did last time, we find out what each of the mass numbers for each of the single elements are in the compound. Hydrogen, it's 1, and there's 2 of them, so we times it by 2. And for oxygen, it's 16, and there's only one of them, so it's just times 1. Add those things together, becomes 18.
And that's molecular mass. It's something else pretty much exactly the same, but a little bit more complicated. Is formula mass, and that's basically this, where instead of just being a simple molecular thing, it's a giant molecular thing. Now later on in the course, you'll be learning about simple and molecular things and which one's which, but for now, just take our word. We're now doing formula mass. So Triv, we have sulfuric acid.
Yes, we do, and the equation of that is H2SO4. Now, we already know that hydrogen got a mass number of 1, sulfur is 32.1, and each oxygen is 16, but there's 4 of them, so we times it by 4, and this gives us 64. You add all these numbers
So you
together.
simply add them all together. We have 2 plus 32, which is 34. Oh, 0.1.
Oh,
I like it, this kid. 34.1 plus 64, which is the, oh god, 98.1. Maths.
Yeah, it's fine, it's chemistry, you got a calculator in the exam, it's okay.
And again, it's just, you leave it as that is your answer. Some of these questions can be 2 marks, normally one for dividing it upright and doing 2 times that, 1 times that, 4 times that, and then a mark for the answer, yeah.
Next we're going to go on to some more complicated equations involving moles, but not the ones in the ground.
And now we move on to something called the mole. There was this chap called
Avogadro.
and he came up with this idea about moles. So what does it really mean? He came up with a number, but what does this number mean, Triv?
Well, this number is 6.02 times 10 to 23, and it's a measure of substance. 1 mole is how many atoms of a molecule are in a molecule.
That's right. This number is really useful to remember because it won't be given to you in the exam. You'll just need to say that's the number. But moles aren't just for stuff like atoms. You could have trivs. If there was 1 mole of triv, there would be that many trivs. And something like oxygen, you could say we have 1 mole of oxygen. That simply means you have this many of these. But this is O2, so be careful. That actually means you've got 2 times that numbers of just oxygens. So don't trip yourself up. 1 mole is that many of something.
Yeah, and this is very useful in many equations. We'll go through, I think, the main solid one now.
Yeah, we'll go through that now.
And that is moles.
That is what stands for moles, this little N-shaped.
Yeah, which equals mass of something over mR, which is
The molar mass. And the molar mass is quite simply the top number, the mass number we went over earlier. So if you look in your periodic table, just say for a second we're doing it on oxygen and you've got 32 grams of oxygen. If you look in your periodic table, you can see the MR is 16, so it's just 32 over 16.
which gives you 2 moles
2 moles.
of oxygen.
So that in itself could be 2 marks. It then might go on to say, so how many atoms of oxygen is there? Well, 1 mole is that, you've got 2, so you just do 2 times that, and that's how many atoms of oxygen you'd have in this particular instance. Crops up all the time in chemistry.
It does
all
apart
the
from
time.
many other questions as well.
As well as waters of crystallization.
Yeah,
it comes up time and time again. Even in Unit 2 chemistry,
It does come
it
up a
comes
little
up,
bit.
it comes up
So
time
it's a
and time.
good thing you need to have names, really.
There are other equations for moles. This is the one for solid. This is sort of the general one. You get one for solutions and one for gases.
Yeah.
We'll come on to that. That's way down the line.
But if we go for an example, perhaps using the equation.
Yes, we'll go through an example now using the solid one you've just learned. So mass over molar mass to work out the amount of moles or something.
Yeah, so if we have magnesium and we put it in hydrochloric acid,
Put it in hydrochloric acid.
then we, well, it's one of the equations you should know quite quickly, as it's a group 2 one of those. It's MgCl plus hydrogen. And we'll just quickly balance this. It'd be 2 of those.
So we have something called stoichiometry. That's probably a new word to
Yeah, it
use.
sounds a bit scary. But what it basically means is the molar ratio from here to here.
So there's actually one of these and
Yeah.
two of these. So what that really means, if we know the MR of magnesium is 24.3 from our periodic table. So if we do
Make a small table of all the things we know.
make a small table, and say we're applying it to this. Now we might have been told in the question that we have exactly 1 mole of this.
So it's a 1 there.
Because this is 2 and this is 1, to get from that to that, it's half.
So we have to divide by 2.
This would be half of the moles here. And that's where this comes in useful, this stoichiometry, this relationship. And it's also important for you to be able to balance your equations, I would suggest. Get very good at that, because then you can do this thing, then you'd know your MR.
So then using this stoichiometry idea from these things, you know how these two numbers, now we can work out
Mass. Now, rearranging the equation is something else you've got to get quite good at. We have moles equals mass over molar mass. We're now trying to work out mass. It's going to be moles times MR. So, half
times 24.3 is 12.15 here.
grams. And these are the sorts of questions you might get asked as well. So this is a really important thing to sort of sum up. So I'll urge you now, we'll go through it all at the end, but I'd urge you now, if you have questions about this stuff, to put it in the comments below.
And we'll try to answer.
This is really, really vital.
And next on to the fluid equations.
The fluid equations and then the gas equations straight after. This is quite a hefty video. Alright, and now we're on to liquids and gases with the mole equations. So first we'll do liquids, because it's the order in the book and just seems a bit logical to do that first. So Triv.
Right. Well, the equation is N equals C minus V, where C is the concentration and V is the volume.
Now concentration is in moles per decimeters cubed. Now how do you write that? You put mole decimeters to the -3. If you see this -3, it means per decimeter cubed. So
It's like writing moles over decimeter.
yeah, that's what I'm trying to get across. That's what this means. So if we're to do this equation, volume has to be in decimeters cubed. Sometimes it's fine, sometimes in the question they'll give it to you in decimeters cubed, but sometimes they give it into you in centimeters cubed. So what do we have to do to get from centimeters cubed to decimeters cubed, Triv?
Well, you have to divide by 1,000.
To divide by 1,000.
So we'll go for an example now. Say if we had some acid, some hydrochloric acid at a concentration of 2 moles per decimeter.
Yeah, you might be something. It's normally an acid like a sulfuric acid or hydrochloric acid. They might say it has a concentration of 2 moles per decimeter cubed and a volume of 500 centimeters cubed. So the first step to answering this question is getting this centimeters cubed into decimeters cubed.
So as you remember, we divide this by 1,000. And that gives us
0.5 decimeters cubed. Now we can go ahead and apply C times V to work out moles. Concentration of 2 times volume, 0.5, is just 1 mole, exactly 1 mole. Again, like the previous equation for moles, you might have to rearrange it. You might have to work out concentration, and again, you'll have to use stoichiometry. The way we did it before, we were given the, I think we used hydrochloric acid. Yeah, we did the hydrochloric acid, and we then worked out the solid. Or it might be the other way around using stoichiometry. You'll have to be using these equations and rearranging that.
yeah.
So make sure you're good at the general mole field. Now let's move on to the gases side again. There's another mole equation. So what is it, Triv?
Well, moles equals volume over 24, but only if they are both in decimeters cubed.
Another way of saying that is this 24 is in decimeters cubed. So for it to work, the volume has to be in decimeters cubed.
If it wasn't, however, you could just change this to 24,000. It would get rid of the dividing by 1,000 step.
That's right, you can do either. If the volume is in centimeters cubed, you can divide by 24,000, and that gives the same thing, or you can convert, like we did here, from centimeters to decimeters cubed, and then work it out with the 24. But just remember, this is decimeters, this is centimeters cubed. So depending on your volume, you use either 24 or 24,000. So this is for gases, and often, I'd say most often, the gas they use is hydrogen. It's usually hydrogen that's given off.
Yeah, so like
in terms of these questions.
the equation we had earlier.
So let's again say for a hydrogen gas, 500 centimeters cubed of this gas was given off in a reaction. Now it's in centimeters cubed. Now we can do what we did here and convert it into decimeters cubed and divide by 24.
Or we could put the volume over 24,000. I go through this one because we've done the other one before.
Yeah, I think so. That's a good idea. I feel we're going to need a calculator for this. 500 over 24,000.
I reckon we might win.
I'm going to get a calculator. I have a calculator. I have my graphic calculator.
50 quid.
So we have 500 divided by 24,000.
And that equals?
0.021 moles. So that implies that in a question where there's reaction and this much volume of hydrogen is given off, there's that many moles of hydrogen in that reaction.
And that pretty much sums up this half of the equations, I think.
I think that's pretty much the equation. This is all of the basic stuff. Get this nailed into your mind because it will come up again
Comes
and
up a
again.
lot.
This one especially, titrations.
Yeah,
You need
core
this.
practicals.
Core practicals. Gases is generally just exam
exams,
equations.
really.
But
Yeah, I think now we should go on to periodicity and groups. In chemistry.
right. So what have we done today?
We did chemistry.
Did chemistry. We started off with a revision of GCSE. We did
We looked at
mass number, atomic number.
or uncommon number, and the parts of an atom.
Yeah, the nucleus, the protons, the neutrons, and what it all means relative to each other. Then we moved on to ions and isotopes.
We did, and we spoke about isotopes being atoms with different numbers of neutrons.
Yeah, and ions are just different numbers of electrons. It doesn't actually affect it when you write it in the form like this. It doesn't change anything.
As electrons aren't really represented there.
No, but a positive ion is where it's lost an electron.
Negative ion, where it's gained an electron.
Because electrons are negative.
I'm really, really annoyed at everything.
Yeah. Then we moved on to atomic
calculations.
mass. Yeah,
Yeah.
we did the well, our example was bromine, wasn't it? It was
Yeah,
bromine 79 and bromine 81, I think.
it was, yeah.
And
We worked out the percentage abundance of each, and then we found the relative.
often
Atomic mass.
the question in the exam is often actually 3 different isotopes.
Yeah,
It's the same thing. It's just
just in 3 parts.
the percentage over 100 times the number plus and then over again.
Yeah.
Then what did we move on to next? I can't remember. It's been a long day.
Yeah.
A massive day.
The equations with solids.
I think so. I think it was the mole equations in solids. Moles equals mass over mole mass. We did that.
Yeah.
And the special number, what is it?
Oh, good old Avogadro. 6.02 times 10 to the 23.
That's magic. That number's magic.
That is magical. Superpowers.
Very big number. It's hard to imagine it.
Yeah, if that was that many sand grains, they would cover all of Great Britain. I think it's
9 kilometres.
9 kilometres in the air. Yeah,
And that's the grain of sand.
they're quite little, so that is quite a lot.
It's really hard to imagine, but it's a big number, and that's what you've got to sort of try to appreciate. Then we moved on to the other equations for moles.
We did all the fluids.
Liquids and gases.
Yes. So the liquids one, we have moles equals volume times concentration.
Concentrations in mole per decimeter cubed, so always convert your volume into decimeters
Yeah.
cubed. Then we did the gases, is moles equals volume over 24,
If they're
or-
both in decimeters.
or 24,000 if they're not.
Yeah. Use some examples for that.
Yeah, we did. We mentioned something called stoichiometry.
Yeah, and that's the molar ratio in an equation, which is quite helpful.
Well, you need that. When you learn, we'll go on to in a bit, sort of explaining how you know how much of each thing's in each thing, so you can actually formulate your own equations,
Yeah.
and then you can do stoichiometry. Because I've actually come across a 20-mark question altogether, and it started off with something simple like formulate an equation, and the next step was then moles using that equation, and something else using what you just did, and it piles up. If you
Yeah.
miss the beginning, you've lost
Yeah.
ridiculous
Sorry,
marks.
going to take a lot of time as well.
Oh,
Often they'll say in the exam, instead of calculate, they'll say determine, and that means you'll be using stoichiometry rules.
yeah, that's right. Big stress, can't stress enough. Definitions.
Oh,
I was going to say equations.
You were.
Definitions. Can't stress enough how important they are.
if nothing else, they actually explain pretty much what you need to do in some things, more later on, but
You know, when we come to stuff like ionisation energy, that definition, not only could it be up to 3 marks, it can be much more than that. When you know that, you know what it
the rest
is.
of the question.
You can rule your way
Yeah.
through the question.
Apply it.
Yeah. So can't stress that enough. You've got to learn them. We're not going through them because there's no point in us telling you them.
it'd take a very long time of video time just to read them all out.
It would. There's a lot they can choose from, and although 40% is a lot of your grade, it's only
Easy
about
marks.
it's only about 10% of all of the ones they have in the book for them to choose from. So
Yeah.
learn them all. They could all come up. I think that pretty much sums up the video.
I think that does, yeah.
Like we said earlier, we've gone through this very quick, and we've only sort of gone over the basics as good as we can, but different people struggle with different things, and it would take forever for us to explain everything
Yeah.
as in class detail.
However, if you have a big question or something that confused you in a video, if you write in the comments down here, we'll try and answer.
We'll try and answer. And if lots of people have the same question of something we haven't gone over, we will make another video for YouTube. But if it's in the
Yeah.
comments, if you leave us an email address, we will send you the answer personally if it's just for you and you're struggling with this or this.
Yeah.
We'll do that for you. But for now, this is Chemistry 1. This is the first bit of Module 1 of Unit 1 of AS. It's
OCR.
mad. OCR.
English.
If you are doing EdXL or anything else, by the way, for chemistry, again, give us your questions. Although it's not the same syllabus we're covering in our videos, we'll be able to try and help you as much as we can.
Yeah.
This is Wayne Lack and James Trivett. It's been a long day.
Until next time.
Goodbye.
It's been a long day.